So here's an example. We want to evaluate this line integral 8xyz ds over curve C, where C is this vector valued function. R of t is 3i, so constant times I, plus 12tj plus 5tk, and t goes from 0 to 2. So in other words, this curve starts out at the point 3, 0, 0, and winds up at the point 3, 24, 10. And so how do we do that? Well, our 8xyz is going to be 8 times x, which is 3i, so 3. I said 3i, I meant to say x is 3. Y, which is 12t, so there's the 12t for the y. And the z part is 5t. And then times the square root of the length of this r, right? Or actually, the square root of the length of that r prime. I keep forgetting to say that. This is the length of the derivative of r. And that's what shows up here. And of course, our limits of integration 0 to 2 are dictated by the curve C. So if we multiply all this out, that's 24 times 12 times 5. How about 24 times 60? And then times this 13, right, square root of 144 plus 25, square root of 169, which is 13. So we got that 13, times that 5, that's 65. Times that 24 times 12, that's 288. So it's 65 times 288. I hope that turns out to be 18,720. And then this t times this t makes it t squared. So what looked like a line integral is eventually converted into just a regular definite integral with only one variable. And of course, that's pretty easy to integrate. 18,720 times t cubed over 3, and t going from 0 to 2. When you put in 0, you get 0. When you put in 2, you got 8 times 18,720, which turns out to be, forgot to say over 3. So 49,920. A nice, easy numerical answer. Okay, here's another one. Evaluate the line integral along a given path. The line integral is just of x squared plus y squared, and the path is going to be the fun part, the curve from 2, 0 to 0, 2, counterclockwise on the circle from the circle x squared plus y squared equals 4. Circle of radius 2, center at the origin, so from 2, 0 to 0, 2. So in other words, we're going across the arc of a quarter circle in that quarter circle that's in the first quadrant. And so maybe this is obvious, I hope it's obvious, our parametrization of that curve is very simple, because since it is a semicircle, we can just say 2 cosine ti plus 2 sine tj, and our t goes from 0 to pi over 2. Granted, that's not the only way to do it, but that's a nice simple way to make this curve up. So then what do we do? This is our x of t here, this is our y of t here, and we want to evaluate this. So we're going to have 2 times cosine of t squared. So our x squared is this squared. So we got 4 cosine squared of t. We're going to have y squared, so 2 times sine of t squared, so that's 4 sine squared of t. Notice this is just 4 times cosine squared t plus sine squared of t, which is 4 times 1. Under our radical for the ds part, we're going to have the square root of the derivative of this term squared plus the derivative of this term squared. The derivative of cosine is negative sine, so we'd have negative 2 times sine of t squared, and then plus derivative of this one, 2 times cosine of t squared. So what we wind up with is, under this radical, is the square root of 4 times quantity sine squared theta plus cosine squared theta. In other words, square root of 4, which is just 4. Sorry, square root of 4 is 2, my fault. So we got this 4 times this 2, we have 8. And 8 dt. So it's 8t when we integrate. T going from 0 to pi over 2. When you put in 0, you get 0. So when you put in pi over 2, you get 8 times pi over 2, which is ultimately 4 pi. By the way, for any parametrization of the form x of t I, y of tj, z of tk, in the line integral formula, our ds is the length of r prime of t, so the square root of, oh, that should be x prime of t squared. Sorry, I have a typo. I'll try to fix that here. It should be x prime of t squared. Oh, what happened there? I got the prime in there. Y prime of t squared. I don't know why I'm going off the beaten path here. And z prime of t squared. There. So that should show up properly, just like we did the same thing when we filled in this ds. Okay.